Hello, this is the next video in a playlist that I'm calling Probability Measure, and here we're going to show that the Lebesgue-Stieltjes measure on in space is a generalization of Lebesgue measure on in space. So for a given distribution function f going from Rn to the reals, the corresponding Lebesgue-Stieltjes measure on the right semi-closed interval a to b, remember these a and b are vectors in space. So the Lebesgue-Stieltjes measure from the right semi-closed interval a to b, we just generically call f of ab because there's a distribution function that is a one-to-one correspondence with the Lebesgue-Stieltjes measure. A and b are vectors in space, and f of ab, this right semi-closed interval, it's the difference, the indifferences of this distribution function, and so we take the difference in each component, and this is how we're going to define the Lebesgue-Stieltjes measure. And I'm going to have to point you back, see a video, distribution function in space, for when we look at these difference operators. Now mu, so first of all, the Lebesgue-Stieltjes measure, we're only defining it on right semi-closed intervals. That's it. Then it's easy to extend the Lebesgue-Stieltjes measure, so mu is extended to a field of right semi-closed intervals. If we let I equal the sum of I sub I, so these are where I are disjoint right semi-closed interval, then we define the measure mu of I, which is this overall set. It's actually the sum of these, the measure of the disjoint sets. And actually in this video, distribution function in Rn space, we touch upon this, where you can break up intervals into disjoint intervals, and then the measures, the overall measure is the sum of the measures, and we give a heuristic proof of that. So note also that it can be shown to be countably additive, similarly as when n equals to 1, or when we're in the reals. And we proved that in a previous video when we were just in the real numbers as opposed to in space. And the proof is so similar that we're skipping it. Now then mu, the Lebesgue-Stieltjes measure, is uniquely extended to a sigma field by this. It's the infimum. So the measure, the Lebesgue-Stieltjes measure of A, is the infimum of all sets that cover A, right? And so we find all of them, and then one of them is going to have the smallest measure, and that's what we take, and that's the measure of A on this sigma field. So where A is in the sigma field of Rn, which are the Borel sets, the Borel set of Rn. Now here's an example. Let f1, f2 to fn be distribution functions on the real number line. Then we're going to define a function in space, f of x1 through xn, just to be the product of these distribution functions. Right? Then f is a distribution function. We're going to prove that, and we must show that f is increasing and right continuous. Now one note for each I, so the interval from AI to BI, remember this would be in the real number line, so it's a right semi-closed interval on the reals. Then the corresponding distribution functions, and so I should have an I here, right? Because these correspond to these distribution functions, right? So when we're in one space, they're distribution functions, and so when you take the difference of those values, it is greater than or equal to 0. Okay, so now let's look at, that's just the fact of the background. Now let's look at the overall measure of the right semi-closed interval in space. And this is defined as using the difference operator. So you take a difference operator on each component of f of x, which is of the distribution function, or at least we're proving it's a distribution function here. So then, but since it's really the product of these individual distribution functions, then you can break it up into the difference operator of f of 1, the difference operator of f of 2, all the way to the difference operator of f of n. But each one of these are, univariate distribution functions, and so it's really just, the difference of those distribution functions. That's what this was, and then 2 is not in here, but then the nth one is this. So it's really the product of these. But each one of these is positive because it's a distribution function, or non-negative, I should say. And so the product of these non-negative values is non-negative, which is how we defined an increasing function in Rn space. Okay, so now to show that it's right continuous, let the vectors approach x, and perhaps I should say equal to there, but it's not, which means that each component in these vectors converges to the respective component. That's what, when the vectors converge to a vector, it has to do it component-wise. And so this is saying that each component converges for each I, 1 to n, as j goes to infinity, right? Then we know that, f of xj is the product of these f's, f1, x1j, etc. That means, and since for each I, so this one, for instance, converges to f of 1 x1, not j. So it converges. That's what it, and the right continuous. So that's what it means. So thus, f of xj converges to f of x, and it's right continuous, right? Because the product converges, and hence is right continuous, and it's a distribution function. Now, if in this example up here, if we let f of I equal x, then, for each I, this corresponds to the Lebesgue measure on the real number line. And so for Rn space, f of x1 through xn is just a product of x1, x2, etc. And then the measure of this right semiclosed interval, f of ab, is actually just a product of those numbers, which is volume, and it's called Lebesgue measure on the Borel set in n-space. Now, more on this later. If we let f be a non-negative function from Rn space to R, and this integral is finite, we can define the Lebesgue-Stieltjes measure of f of ab as the integral of f, in n-space, over this right semiclosed interval, which then Fubini says we can iterate it so it's equal to this. And then we can show there's a one-to-one correspondence between Lebesgue-Stieltjes measure and distribution functions, f. Now, more on this later if there's an interest to do integration in measure theory, then we will really hit this hard. But for now, that's it. And hopefully you enjoyed this video. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.